This is the last video in the series of lecture videos for 4.3 linear independence. And I just want to wrap up with a couple little examples here. Should go very quick. First example, we're saying are the sets of functions in P2, remember P2 is the set of all second degree polynomials, is the set of functions linearly independent. In this first part A of the problem, we have the set of functions f and g, where f is defined to equal 2x squared plus 1, and g of x just equals x. So if we ask, is this set of vectors, really they're just functions, linearly independent, I'm going to claim right away we can just say that yes, this set is linearly independent. And I want you to try to think about this and see why we can just look at these two functions here and without doing any work at all conclude that they are linearly independent. Think about that. Consider it. You can go through the actual process that you'll see in part B for determining the answer kind of systematically. But I think this is one where we can look at it and just say, yes, these are linearly independent if we think pretty critically. If you have trouble figuring out that leap there, feel free to get in touch and we can talk about it. But I'm going to jump to part B so you can see sort of the systematic way you can handle it. In part B, we have three functions, f, g, and h, where f of x is negative x squared plus 2x plus 1, g of x is 5x minus 1, and h of x is 7. So the question is, are these three functions linearly independent? Well, we know that to check for linear independence, we have to set a linear combination of these three vectors equal to 0 and see what sort of solutions are possible for that set of scalars C1, C2, and C3. So we're going to write this out. We're going to say C1F plus C2G plus C3H. We're trying to see if that really equals the 0 function, right? Or if we can find a solution C1, C2, C3 so that that equals the 0 function. And once we find that solution, we can figure out the answer to the problem based on that solution. So let's write down what this equals at a specific x value, or a general x value, I should say. This means C1 times f of x plus C2 times g of x plus C3 times h of x would equal 0 regardless of the x value for all x. Now expanding what f, g, and h all equal, this tells us negative C1 x squared plus 2C1x plus C1 plus C1, sorry about that. That's just this piece. That's just the C1 times f of x expanded out. The next piece gives us C2 times g, 5C2x minus C2. And finally C3 times h, that's just C3 times 7. We're saying all this equals 0. And here, maybe to make things clear, let's go ahead and gather up coefficients on like powers of x on the left side. We have negative C1x squared plus 2C1 plus 5C2 if we gather up all the coefficients on x itself, leaving just the constants C1 minus C2 plus 7C3 to equal 0. So maybe I'll go back up here and see this. Okay. Down here now, if we continue, all we're going to do to solve this system for the c values is to equate the coefficients of like powers of x here with the same coefficients of the same powers over here. So for example, when we look at x squared, we've seen this a little bit before, we get the coefficients of x squared on the left are negative c1, on the right it's 0. There are no x squared terms over here on the right. Jump back over here, look at the first powers of x. What coefficients do we have? We have 2c1 plus 5c2 on the left side. That's what's multiplying x on the left side. There are no x's on the right side, so that's a 0 there. And all the way down to the 0 powers, or the constants, we have c1 minus c2 plus 7c3 equals 0. So we are looking again at a system of equations. Let's see if we can solve this. I'll pack this up, or maybe even not pack it up. We can just say, we don't need a matrix at all. C1 must be 0. That implies that C2 must be 0. Plugging into the second equation here, right? C1 equals 0. Going in here tells us C2 must be 0. Well, if both C1 is 0 and C2 is 0, plugging in here tells us C3 is 0 as well. Let's write that down. So, what we have found is that the only solution to this equation up here, this linear combination of f, g, and h to equal 0, requires that all three of those scalars is 0. Each of them must be a 0. So we can conclude, maybe take a second, see if you know the answer here. Is the set linearly independent? Yes. The set is linearly independent since C1F plus C2G plus C3H equals 0 only is satisfied by all three scalars equaling 0. Okay, that's it for this section. Stay tuned for more coming up in the next section soon.